How are you doing? Thank you for being here. So my talk is going to be about what we want to do and what we do to secure ground station. Okay, and actually, what I think we need in general as industry, like technology, that we have been used in other contexts, right? But they are rather new here. Okay, let me introduce why I think we need these things by telling you what we do, and then we go on with the things. Okay, I work at LeafSpace. We are a ground segment as a service. Okay, we are relatively small, but we are growing. Okay, and as we grow, we need to expand our network and to take care of the security. And I'm gonna tell you the things that we're gonna take it into account of security also from an internal perspective. I'll get back to that. What we do is we don't launch satellites. We don't do even operations, right? What we do, we have a set of antennas all around the world, okay, that a customer can rent, okay, to communicate with their own satellites, okay? And the customer encrypt the data, so we don't look at the data. We don't need to have there. We can just deliver the data from the satellites through radio communication, right, to the customer, okay? And that's the thing that we do, okay? We don't launch, we don't operate, we just deliver data, okay? We have multiple services. I'm not gonna bother you with the services. If you want to know about the services, you can go on the website. One can be getting the data, but also tracking during the launch, okay, of a mission with multiple frequencies. So with multiple radio, and that matter. And this means that we have multiple decoders on our antenna to handle multiple frequencies, multiple protocols, okay? We can do that, okay? This is our map today. We have more than 20 ground stations. We are building new ground stations every day, and they are very far, okay? So we don't have physical access every day to those locations. Some location is pretty hard to reach, okay? So we do have support there, okay? But we want to avoid to be there at any time, okay? So we need that stuff to be and stand all the time without us being there and checking, okay? This brings a certain threat model to what we do. So first of all, to have all the antennas communicate with us, we basically build an internal network using cloud service, okay? And so the antennas connect to our network, and then we deliver through our network to the customers, okay? This means that basically we have two entry points of data in our system, okay? One is from the customer, the other is from the satellites, the satellite perspective. Okay. Ideally, we want the data to be encrypted so that we don't look. We only deliver the data so that we don't look at the data. So that's not part of our threat. I have a list of what are our threats, okay? But the main problem that we have is availability, okay? We need to guarantee to our customers the service, okay? The data is encrypted, so we don't have a confidentiality problem, unless crypto is weak, okay? But that's not on us. We may have integrity problem, but this can be solved with the correct encryption as well. But availability is on us, right? Delivering the data is on us. That's our main threat, okay? And we have, so if you take security of this system from an external perspective, right? We have two entry points. We have the API that we expose, okay? But we also, and that's the other point, we have the data from the satellite, okay? And so we of course don't trust whoever is coming from the API that's exposed to the internet, but we should also not trust what is coming from the radio in this case, right? That is the satellite or whoever is close to our antenna in the world. That is there, okay? It's confined, but we cannot confine radio signals, okay? So that's another threat that we have, okay? So we do testing and penetration testing here, but from the radio, okay, the data is coming through the radio, through our decoding system, okay? And that's something that we should care about as well, okay? If you only care about the perimeter, at some point you're gonna fail, because as soon as one goes through the perimeter, for many reasons, okay? Misconfiguration, someone didn't sleep and clicked on a wrong email, whatever. At some point, someone gonna be in your network, okay? And if you only check the perimeter, when they are in, they are in. And it's really hard to find it and to discover, okay? So what you actually want to do is not just monitor the perimeter, but also monitor the things that you have inside the network. If the things are confined and are secured per se, okay, then even if someone get through something, okay, then you can still confine the attack. And in this case, for us, it means identify. I mean, there are many things that you can do, but my talk is going to be about identify the vulnerability on the forgotten component, okay? What is the forgotten component in our system is the binary decoding the radio from the satellite, okay? You need to be fast decoding the radio, so either you have specialized hardware, and if it's not specialized, you have like software-defined radio, that is basically gonna be compiled code, okay? Maybe from us, maybe from a third party. It doesn't change the threat model. You have binary running there on a remote system. If you have a vulnerability there, someone that is close with a radio can ideally exploit that. And to be honest, it doesn't need to be that close, because ideally, I mean, we are getting data from satellite, so you can be far sending us data, right? Okay, so that's the point. So what I'm gonna discuss is basically how you find the vulnerabilities, okay, in automated way. And this is how it's been done and how it's been doing it in the IT sector in general, right? We have been doing that a lot and this has been a very successful, okay, attempt to automate finding the vulnerability. What is the concept of finding automatically vulnerabilities? Is you have your binary, okay, that is running somewhere. In our case, it's the ground station. It can be whatever. It can be whatever you are running on a satellite. It doesn't change the concept there, okay? The idea there is that you try to generate some input that generate a crash, okay? A crash of a binary is a vulnerability. At least a bug, okay? So if you have a binary and the binary crash at some point, it means that you have a bug. There is no reason for a binary to crash if it doesn't have a bug, okay? So if you manage to trigger a crash, you have a bug that probably is gonna be a vulnerability. So you want to remove that, okay? And this is something that we can identify automatically, and that's why it's interesting. Okay, because if you run the binary with data and it's crashing, you can monitor that through your system. Okay, so this is something that we can use to monitor the things. Now there are basically two ways usually in techniques that you use to identify the vulnerability automatically. I usually put it on like a spectrum, okay? From one side, you have fuzzing, okay? And the concept is very, very fast random data with quotes, because it's not really random, okay? So that you can try to trigger to trigger crashes, okay? And on the other side of spectrum, you have the smart version, okay, that is symbolic execution. So you do, I'll tell you what is symbolic execution there, but it's considered the smart version. And to be honest, there is a lot in the middle of this spectrum, okay? So what is the idea of fuzzing? Fuzzing is I generate random input, okay, and eventually I'm gonna crash the my binary, okay? Random input, keep generating random input and crash the binary. Random in this case is a problem because if you keep having random binary, random data, it's really, really hard to find the correct random data. The space is huge, right? You are searching in a huge space. So what you want to do is actually guide this generation of random data through something that is meaningful, okay? What is meaningful in our context is the amount of software that we could actually execute and excite with our input, okay? So the idea there, it came from software testing. The idea is I try to test as much as a path in the code that I have, because if one path is vulnerable or is not correct, if I execute that path, it's very likely that I'm gonna see the crash or the vulnerability on what is it, okay? So what people have been doing is not fuzzing per se, so generating only random data, but is guided fuzzing, okay? And the guidance in this case is done by the code coverage. How much code I can cover going through the execution. How I measure that? I execute the code and I count, right, how many blocks I visit in the execution, or better, how many edge, so the connection between two blocks, okay, I can actually execute, okay? That's how. Does this tell me that I visit everything? Does this allow me to find all the vulnerability? No, there is no such thing of finding all the vulnerabilities, but it tells me how much coverage I have, and it's a good indirect metrics into finding the correct spot, okay? How you do that? There is basically, you can embed this search for coverage through how you generate the data, okay? You don't generate random data. What you try to do is to actually mutate data that you consider interesting, okay? So I don't know if you're familiar with like genetic algorithm. Okay, it's very, very similar on what you do in genetic algorithm. You have a set of good input that triggers nice thing, okay, and you mutate that, okay? And if this mutation brings you an upgrade on the coverage, okay, then it's a good input to keep and keep mutating, so to cover even more. There is a trade-off here. If you do low mutation, then you're not gonna cover enough code. If you have an aggressive mutation, then it's basically random and it's hard to find, to explore the space, right? So it's a trade-off there. There is a set of well-known mutation that have been implemented that works pretty well. I have a list here. I'm not gonna go through all the details, but some are kind of obvious. There are numbers that are very good at triggering vulnerabilities, like 0, 1, -1. Okay, those are the nice number that usually breaks systems, right? So you try those, okay? But you also try, for example, to take two inputs that are good and try to mix them together, okay? Or flip random bits in the input, right? Those are all things that have been proven, that have been used to generate a good amount of code coverage. We have a lot of tools that already do that. Okay, there is a significant amount of effort. Those are some on people implementing system to do that easily. Okay, I put the list there so that you are aware. There are tools that work standalones, but there are also libraries that you can adapt in your context, right? Because you need to maybe, and I'll get back to that, but the mutation that you do, it depends, right, in your context. Okay, if you have a special protocol, right, doing completely random data may slow you down. So you may want to implement your own mutator that is very specific on what you're trying to parse. Okay, the important things in fuzzing is speed. Okay, the tools are built to be fast because it's the stupid tool in the sense that the reason why fuzzing works is because I can try a lot of input very, very fast. Okay, so the tools are built in a way to try to be the fastest possible. Okay, so there are many modes that depend on what you can do. Some is faster than other, but the main thing you should care about when you implement a fuzzing campaign on your system is you want to be fast. Okay, it's like I'll give you an example. It's like the CPU that we have. CPU are stupid. They do very small stupid operations, but because you do very, very fast, it looks like intelligence, right? Now we call it AI. But that's still matrix multiplication, okay? So it's a similar concept. It's not the same, but the point is very, very fast, stupid things brings a lot of value, okay? And this is what fuzzing is doing, okay? So, for example, you try to not even recreate, so spawn a new software every time. You use a technique that is called forking server. I spawn my binary once, and because I can exploit the operating system to avoid to relaunch the same binary multiple times, because executing a binary is slow, okay? It slows you down a lot. So you may want to implement some wrapper around what you are trying to test to fix that. Okay, and you can scale a lot. There are projects where you can scale your campaign, like in the cloud, very, very fast, so that you can fuzz a lot. Okay. Important things here is the only things that you're gonna notice are crashes. Okay, so you want to have many, many crashes. Normal compiled binary, they crash only when they do a wrong memory access. It means that you are accessing an address, read or write, that is not valid. That's the only thing that you see as a crash in binary. Okay, so there are tools to increase the amount of crashes, okay, that you may have. If you have a buffer overflow in your program and the buffer is overwriting something useless, you're not gonna see a crash, okay? Because you are overwriting something useless, so the program continues working. You still have the vulnerability. This system is not able to detect it, okay? So there are tools in the compiler that change how you compile things. You put guards, okay, depending on the type of vulnerability you want to find, to allow you to find more crashes. You pay in performance, of course, but this is another trade-off where you slow down a little bit, but increase the amount of things that you're gonna find, okay? There are fuzzer that are built on specific protocol. Okay, so if your input is random data, the standard fuzzing is okay. But sometimes you don't have random data. You have a specific set of data that are structured. Okay, so you can try to work only on mutation on that data, so that you are faster in finding vulnerability. Those are some examples of what you can do. Okay. The other point is that when you find an input that crash your system, okay, then it's usually huge, and there is a lot of things that are useless that are not actually triggering your vulnerability. Okay, it's random data, so what is triggering your vulnerability is hidden in this random set of bytes. Okay, so there are techniques to minimize the input. Okay, so that hopefully only the relevant parts are left for you to debug and find the vulnerability in your code. Okay, this is a few examples of tools that you can use. This test case minimization is also called delta debugging. It's classical. I remove some part and I see if it's still crashing or not. And if it's not, then I put it back and I remove something else. Okay, you do it with a bisect approach. So you can do it decently fast in a logarithm time. Fuzzing is limited, okay? And when you have code like this, okay? Let's say that if you reach this point, you are crashing. And you have very specific value here to reach this part of code, okay? This is how much is the probability that you're gonna generate the data to get here? It's 1 over 4 billions, okay? Because this is 32-bit data, okay? So fuzzing will never find this, okay? And that's the reason why there are other techniques to do that are slower. That's what people call symbolic execution, okay? The idea of symbolic execution is that I'm executing the binary not with real value. Okay, this is the real value execution. I put x equal to 7, I execute. This is less than 5, then I only execute this branch. Okay, the idea here is I can do execution with symbolic data. I know this is weird, but there are tools to do that. So I don't really know how much x is actually as value. It's a variable, a symbolic value, okay? And then I do the execution, and when I reach some comparison with this value, what I do, I basically execute both paths, okay? I create some constraint. I say, oh, if I went that path, x was less than 5. If I went the other path, x was greater than 5, greater or equal than 5, okay? And I keep executing with those constraints in mind. Okay? And at the end, when you do this execution, you collect all those constraints, and you can use constraints program system like Z3 to find solution to all your constraints that you collected during the execution. Okay? I'm not gonna go through the SMT solver. That's how you do it. Okay? That's for another time. That's the formula there, but it's I'm very slow on that. There are implementation of this where you can basically combine the symbolic execution with the fuzzer. The idea is that they are running in parallels. So you take one input and you run it through the symbolic execution while the fuzzer is running. And this eventually allow the fuzzer to break through some barrier like the one I show you, where you have very specific value. Okay? Where symbolic execution fails, when you have too many paths. Okay? The symbolic execution split the execution every time you need to check for a variable, so the amount of paths that you have is exponential. Okay? So if you run symbolic execution through big program, you're never gonna reach the end because you have too many paths to consider. Okay? And that's why symbolic execution failed to be the main system to use for this. Just to conclude, so we can take some questions. There are other stuff to do fuzzing on other languages, but usually they look at an handle exception or ANGS, denial of service, because we don't really have crash in Python beside that. Okay, so memory crashes, so you need to rely on that. Okay, the limits that we have in the system is we are relying on the memory model of the CPU to find the vulnerabilities, and not all the vulnerabilities happen because you access the wrong memory. If you have like a logic vulnerability, you're never gonna find it through fuzzing, okay? Unless you have a model, and that's very very complicated. To prove you that works, okay, there is Google running it on a lot of things, finding like thousands of bugs in open source project. Okay, so these have become the standard when you need to test a compiled software in the industry. Okay, just to conclude, I mean, you need to take care of stuff inside. We have techniques to do automatic discovery of vulnerability. It's very scoped, narrow scoped, but it works. Okay, and it works at scale because we can check many problems with their limitation. Okay, I'll take some questions because I'm very late on that.
All right. Thank you very much, Mario. This was a very quick but also very comprehensive introduction into fuzzing.
Yeah.
I really learned a lot. So we have a couple of questions on the app. Let me already pick the first one. So to which extent can you instrument already compiled binaries with sanitizers if you don't have the source code?
Okay, so there are, so basically what you do, you use an emulator like QEMU to instrument the binary. And this is supported already by like FL++. Adding the sanitizer, it's hard. There are a few projects that are doing that, but they cannot be at the same level as if you have the source code. Okay, so there are projects adding sanitizer while QEMU is doing JIT compiling, but it's not the same. So they are a bit limited yet.
Thank you, and thank you, Fabian, for this question. Next question is from Marek. You mentioned several times being faster or slower with fuzzing, and well, speed matters. So what time frames are we talking about for typical fuzzing campaign? How slow is slow and how fast is fast?
So by being fast, it means you want to do like thousands of attempts per second eventually, okay? But you can scale it, like in the cloud, you can spawn as many machines as you want. And you can do it for like 1 hour, or you can do it for months, okay? The cluster fuzz, whatever, it runs constantly on projects, basically for months, okay? It's hard to balance that. You have the resource, you do it. That's usually the approach, but it needs to be day or week.
Okay, thank you. And thank you, Marek, for the question. Next question from Jyrki Huhta. Will Rust be our savior?
Yeah, that's a very good question. So short answer, yes. Okay. Long answer is no. So the point is, memory-safe language are good, okay, and Rust is good in doing that. But first of all, bringing that to everywhere is still gonna take like a decade, probably. So we still need that. Second, it may save us from memory errors, but it will never save us from logic vulnerabilities. So it's a little bit better, but still, it's gonna be a long time. Okay, I hope to be all Rust compliant in 2015. It's 2024, and still we are not using Rust enough.
Okay, thank you. One more question I see from Alessandra. Mario, is your activity potentially to be considered critical for the protection of space ground systems? And if yes, can you elaborate in qualitative terms why?
So the point is, if we find vulnerability fast, then we can fix it, and we don't have a problem. If we ignore the problem, it's gonna we're gonna have a problem in the future, right? So it's inside the network. So it's not directly exposed, but it can be exposed when you have people that is going through your network. And at some point it will happen, so it's better to be prepared.
Thank you. Any questions from the audience here?
What kind of fuzzers or fuzzing technique would you use for testing LeafSpace, for example, ground segment?
Yeah, so basically, I would implement like a protocol-specific fuzzing on the radio that we receive, right? First, we do it with random data, and then you build that's still gonna bring you something, and then you build protocol-specific parser that depends on the protocol that the thing is doing. Yeah.
Okay, thank you very much. Everybody give it to Mario Polino.
Thank you for having
talk.
me.